Alright, let's do some more tangent slopes here. Let's go for tangent slope, second example. That would be this one. So again, what we're after is, pick some point here, 40 degrees, that's a little bit past, it's 30 degrees, and we're looking for the tangent line there. The tangent line is probably something like this. We'll go green, something like that. Maybe it's going downhill. And we're looking for that tangent slope, the slope of that line right there. Okay, and we set out to find it. dy dx, what is it equal to? Again, the key to this is figuring out that you could do dy d theta on the numerator and dx d theta on the denominator. And that makes it a lot easier. Now we just use our definitions, from definition of polar coordinates, to compute each of them. Recall that we had y is equal to r sine theta, therefore dy d theta would be equal to the derivative of the first, dr d theta, plus r times cosine theta, the derivative of the second. And of course that's what goes up here on the numerator. And similarly we had that x was equal to r cosine theta, so dx d theta is equal to cosine theta, dr d theta, plus r times sine theta. And of course this one right here is minus, let's do minus, yeah, minus r sine theta. That's what goes on the numerator and the denominator. So this would be sine theta dr d theta plus r cosine theta, cosine theta dr d theta plus, should I keep doing plus, minus r sine theta. Alright, that's what we have as our formula. Actually, incidentally, this never changes. No matter what the problem might be, this part would always be the same. I haven't even used the fact that in this particular problem, r square is equal to that, or whatever. So a lot of books will just have you memorize this piece right here alone, which is fine if that's the way you want to go about it. I like to know that I own the stuff, or I think it's beneficial if you understand where they come from. These ones come from the basic definition of r and theta, taking the product rule. That's how you get those formulas. Alright, talk is cheap. Let's start subbing things in there. I can see that I'm going to substitute the dy d theta is going to go, sorry, the dr d theta I need to get from here. I've already substituted my dy d theta and my dx d theta. I need to figure out what this guy is, dr d theta. For that I'm going to use my original function here, r square. So here I have that. I'll go right on this one. R square is equal to 30 times sine of 2 theta. And then I'll slap a integral on both sides, or sorry, a derivative on both sides, d theta on both sides. That would get me to 2r dr d theta is equal to 30 times cosine of 2 theta times 2. Or that would get me to dr d theta is equal to, incidentally I think I can cancel that 2 there and that 2 there. Just cleaning it up a little. If you wanted to, you don't have to. This would give me 30 over r times cosine of 2 theta. That's what's going to go here for r theta and for dr d theta on my formula. So this becomes, let's go back to yellow, this becomes sine theta times dr d theta. So it would be times 30 divided by r times cosine of 2 theta plus r cosine theta. All that over cosine theta times dr d theta, again 30 over r times cosine 2 theta plus, no, that would be minus, right? Minus r times sine of theta. Perfect. And we can do better than that. We know what r is. Well, we know what r square is. So here from there I get that r is equal to the square root of 30 times the square root of sine of 2 theta. It's actually plus or minus. Okay. So then what do we go from there? We need some calculators so we can plug in everything. We're going to plug in 40 degrees. wherever you see theta, you get to plug in a 40 degrees, and wherever you see r, you get to plug in this thing with 40 degrees in there. So altogether we have the following. Before I go on, I'm going to clean this up a little bit. I'm going to multiply the top and bottom by r. And the reason for that is because, so I can avoid this whole plus or minus thing, multiplying top and bottom by r would get me, no r's there, would cancel that one. It would get me an r square here and an r square there. And r squares can always be exchanged for a 30 sine 2 theta. So that's going to be advantageous. I'll slap an r on this side and I'll slap an r on that side. That will get me to the following rewrite of my priced formula here for dy dx. That would get me sine of theta times 30, that r is gone, times cosine of 2 theta plus r squared times cosine theta. All that over cosine theta times 30 times cosine of 2 theta plus r, no, it's not plus, it's minus again, minus r squared times sine theta. That's a little better. And then for the r square, I can always exchange that, so that gets me that dy dx is equal to, otherwise I have to analyze, where is it positive or is it negative, which side is it on, blah blah blah. It might get complicated. This cleans up the logic a little bit, makes it very clean actually. So this becomes sine of theta times 30 times cosine of 2 theta plus, here we go, r squared can be exchanged for a 30 times a sine of the double angle times, of course I have a cosine theta from there, all that over cosine theta times a 30 times a cosine of 2 theta minus, I got that one right, 30 times a sine of 2 theta times another sine of theta. Whew. Now what we have to do is we set out to find the tangent slope at 40 degrees. We've got a nice little recipe here for the tangent slope at any given angle, not just at 40 degrees, but you plug any kind of angle here and lo and behold you get the slope of the tangent line. So I'm going to put this into the calculator and we'll crank this out and see what it is when you get 40 degrees. We got the calculator here. I've entered a function here. Sine 30 cosine double the angle plus 30 sine double the angle times cosine, all over cosine times 30 cosine double the angle minus 30 sine double the angle sine. And then I evaluate it at any given point. So for our problem we need to evaluate it at 40 degrees. So I'll put in here 40 degrees, and of course the slope is negative 1.73205, duh. Which means that this slope here, the rise over run, is about negative 1.7. You drop 1.7, you run 1, roughly speaking. But this is an amazing formula. At any given angle, you can quickly find the tangent slope. Suppose, for example, you try to find it at 9 degrees. Clearly, that tangent slope is really, really big. It's steep. It's almost infinite. So you should try it here just for fun. If I try 90 degrees, I should get something very, very steep, close to infinite. And indeed we did get a huge number. Alright, now that's dominating the tangent slope question right here. Nice formula for all the tangent slopes on this curve. We should celebrate here, and right after celebrating we should move on and do some more calculus on polar equations. I'm thinking that next we should do stuff like areas. How about we try some polar areas next?